All right, example 4. A rectangle is bounded by the x-axis and the semicircle y equals square root 25 minus x squared. Find the dimensions of the rectangle that would maximize the area of the rectangle. Okay, so let's just start step 1, optimize. What do we need to optimize here? And they want to maximize the area of the rectangle. Okay, of the rectangle. And so to find this particular problem, we're thinking of it on a coordinate grid, which means we're thinking of it in terms of coordinate points, x comma y. So this is kind of how we have to build this in order to think about what the dimensions of this rectangle are. We can't just be as, I guess, generic or general about it as we were with the last rectangle because it's on an actual coordinate plane. So the way that coordinate planes work, right, we have some x amount to the right and an equal x amount to the left. I know in this particular picture it's at -3 and +3, but that's just like an example. So we don't really know how far out in the left and right. Like if I were to shrink this down, it would stay proportional, or if I were to move it out. So it's x in each direction and then y as a height, right? Which means that really this side length is equal to 2x. So when I'm thinking about the area of this rectangle here, I'm trying to optimize the area of 2x times y. So I somehow want to get rid of one of those variables, and in this case they pretty much just gave me the constraint as a formula. If y has to be, our y value has to stay on this semicircle line, our rectangle can't just end wherever it wants. It has to stay on this semicircle. So that means that the y value can be written as this equation here. So this is our mathematical constraint for our variable y. Okay. So in this case, I'm going to come over here. I'm going to plug that in. Square root of 25 minus x squared. And then I'm going to have to derive this beautiful expression. So I'm going to go ahead and get it ready for that. And write the square root as to the 1/2. And then we're just going to go for this, so buckle up. We're going to take a prime. And we're going to do first times derivative of the last. Well, that becomes -1/2. Oh, now watch out for this one. This gets me all the time. When you derive this, watch out for that negative sign. So it's really going to be the inside derivative of -2x. That is tricky. Plus last. D first. Okay, we're definitely going to use our calculator for this, so you can stop hyperventilating. So basically here, the 2 and the 1/2 will cancel. And okay, that's about it. So we're going to end up getting a -2x times x, which is -2x squared, times, well, let's go ahead and write this without any, I like writing it as like an actual function, but if you're going to type it in your calculator, you really don't have to do that. And then plus 2 times the square root of 25 minus x squared. Okay, so fun fact, because I just want you to see this as possible. You can really do this by hand. I'm going to let you use a calculator, but you could get a common denominator by multiplying this denominator times this numerator, which would make your square roots kind of cancel each other out, so to speak. So your new numerator would be this guy plus 2 times this guy, no longer under square root. And if you do that, you get this for the top and this for the bottom. So if you find where this equals 0, you're going to end up getting x equals plus or minus the square root of 25 over 2, which is gross. But if you do it in your calculator, you're going to get the same thing. You're going to get approximately 3.536. And we don't really need the negative one because that doesn't really make sense with how we're thinking about the way we've drawn it. And then the plus or minus 5, seems tempting because it's a lot prettier than that. But if you go back up to our graph, right, if our x is at 5 or negative 5, that's when the y is going to be all the way down here flat. So those are kind of considered our endpoints, and in this case we know those are not optimal because our entire rectangle would just become a thin line. So long story short, you could find these values by hand if you so choose that adventure. Either way, we hopefully will find that, let's see, a prime equals 0. Well, let's do that. Miss Wright never actually set it equal to 0, did I? We'll say that x is approximately at 3.536. And then we would use our number line to test that. Although, honestly, you don't really need to draw the number line if you're graphing it on your calculator. You can see that it changes from a positive to a negative. We're running out of space. Okay. So now we can actually answer the question, what would be that area of the circle? So again, I would just use a calculator to actually type in, when x is this gross decimal, what do you get for y? And weirdly enough, you actually get the exact same value. And so it's the same exact thing for y. The difference is to write our final area, we need to think of this side length as 2 of these. Okay, so we'll say that the rectangle ends up being 2 of those axes, so 7.071 by the y value, which happened to be the same, 3.536, will maximize the area. And you're going to find this a lot in maximization problems, that the more closely the shape resembles a square or circle, the more optimal the area gets.